Now that I'm recording it, I won't heckle because I don't want to be on record of heckling.
This is an unfortunate room for latecomers.
Yeah.
They gotta come stand right there and be like, oh, excuse you, sir, for coming late. And you can't ignore it, they can't be sneaky.
That's everyone that was going to attend. Do you want to?
Yes. Well, thank you for showing up. Today is the kind of like defense in traditional research-based schools. There is a day that the student shows up here and there's a bunch of faculty members and other folks. They start bombarding the student with questions, hard questions. Today is that day for Travis here. So, well, it was a pleasure working with Travis during the last year and a half. He started the work around summer 2014, and the focus was looking at the water reuse cases in California and in the country. So in the case of water reuse, well, let me go one step back. Well, we are short in water, but what are our options in front of us? Conservation, desalination, and water reuse. We don't have any new source of water in the country. So we got three options: conservation, reuse, or desalination. Well, this work is focused on reuse. Now, in the case of reuse, we get wastewater and we do treatment, primary, secondary, tertiary, and then we put it in a membrane process, like reverse osmosis in this case, and then we use the product water. But we never look at the byproduct of reverse osmosis process, which contains contaminants of emerging concerns, like pharmaceuticals. Those chemicals that people daily use in their daily lives, those chemicals end up in wastewater. After wastewater treatment, it's in reverse osmosis. It's been rejected by the membrane and it's in there. So what are those chemicals? Where in the country or in the world people are doing some sort of measurement, and if they do measurement, what is the level of that contamination? So those are the sort of questions that we defined in the beginning, and then Travis, during this year of work, answered those questions. So he presented in number of conferences so far. He generated a peer-reviewed journal paper. A copy of that is available. We have one hard copy here, and hopefully it's published soon. He works really hard. We had meetings after hours. Our meeting was like 6 p.m., 7 p.m., 8 p.m., late nights. He presented in a national conference about a month ago, American Waterwork Association conference, national conference, and the work was very it catch interest among the audience attendees of the conference. So thank you for being here, and then Travis, is yours.
All right. Well, yes, thank you for coming today. I know it was kind of an inconvenience for many of you coming from very far away. And I know my fellow graduate students actually had a midterm rescheduled so they could attend today. So I definitely do appreciate it. Like Dr. Sharbat said, we were approached by the Bureau of Reclamation about a year ago with the interest of having a graduate student do research to solve some problems that they were encountering on different projects that they're working on across the nation. And it actually worked out pretty well because I had already started down that path with research in other classes. So I've officially been working on the project for a year, but it has a research that I've done over the entire 2 years that I've been in the program. So it's kind of all worked out well. It's a culmination of a lot of hard work. So my project is on contaminants of emerging concern and reverse osmosis brine concentrate from both indirect and direct water reuse applications. And I'll go over a little bit about what all those different big words are about. So the first thing is go over the need for water reuse, why this even matters in the industry. Go over a little bit of a background on contaminants of emerging concern, as well as the research methodology that we went through. I'll then go over the results, which are broken into 3 distinct sections: list of CECs, different treatment methods, and pertinent regulations. Then I'll go over a conclusion, as well as the implication of this project and what's going to occur after it. So as many of you know, drought is nothing new in the United States. In 2011, it was very, very concentrated in Texas and Georgia. This was the time when Georgia tried to relocate the northern boundary of their state in order to get more water rights, and Texas began the thought process of water reuse. A year later, that moved north up into the Midwest, and flash forward to today, it's very, very strong in California. It's actually reached a point where in January of this year, 100% of the state of California was defined as being in a drought, with somewhere around 80% under a severe drought. So this is a very, very big concern right now. The Sierra snowpack is actually at 8% of what it normally is. I was in the Sierras just a couple weeks ago and took this picture. This is one of the high altitude lakes. The water is about 30 to 40 feet low, and there's very, very little snow in the watershed above. So it is a very big concern. As many of you probably hear nightly on the news, California has issued mandated water restrictions as a result of this very bad sign of what's coming. They were issued on April 1st and have been finalized as of the past week, so it is a very big concern. Right now, like Dr. Shabbat mentioned, there's three different options: conservation, desalination, and water reuse. Conservation is already well underway, but it's not going to be enough water to meet the goals, so we're having to look at other opportunities. Desalination is a very, very popular one, but unfortunately, there's a lot of issues with it. It's very expensive, the systems corrode really well, there's an environmental concern. So a lot of agencies are looking at water reuse, which is turning wastewater back into a usable form, getting closer and closer to turning it into drinking water. Now, one of the biggest pushes in water reuse is the use of reverse osmosis. It's a proven system, very effective. It's well known how to run the systems. It uses pressurized pumps to push water through a membrane. The water comes out clean on the other side, and the membrane catches all of the contaminants. The one major drawback to this system is the brine flow that is generated as a result of cleaning the membrane. This can be a fairly sizable flow rate. They use about 15 to 25% of the water that passes through the RO membrane to put back into the system to wash the membrane off and drain it off on the side. It has all of the contaminants that were in the original amount of water, but at about a fourth of the flow. So the concentration levels of all the contaminants are very, very high. And amongst these contaminants are contaminants of emerging concern. These are chemicals that were used for their intended purpose and then released into the wastewater. Hormones, steroids, pesticides, pharmaceuticals, and personal care products such as makeup, things like that. It's a little bit more common to see things that are ingested by humans rather than the pesticides or things that are just put onto your lawn, but all of these are found in wastewater flows. So CECs are known to have a major health issue. They have been found to cause the feminization of fish at treatment plant outfalls. This has been reported in multiple studies, and in probably the most famous case, DEET was accused of causing renal failure in vultures in Northern California. This was the push for the California condor becoming an endangered species. That's all one of the main attributed attributes causing that was DEET, which is an industrial chemical. CECs are known to occur in conventional water treatment plant outfall, but the levels are typically not too concerning. But when you concentrate them into the RO brine, it becomes a really big issue. So when I started looking into this, before I'd even heard about this project actually, we found that there's no comprehensive database on any of these issues, especially what CECs are in the water, what their concentrations are. There's just scattered tests, that's it. There's also no comparison of different treatment options, largely due to the cost of studying it. It's just one treatment test and they present the results, they don't compare it. And there's also no comprehensive knowledge on the regulations that are in place. So we began by looking at those scattered test results from both lab tests and full-scale testing at treatment plants and started combining those into a single report. We also did a field poll to determine what knowledge is out there that the industry has that isn't published or isn't really known on a wide-scale process. And we tried to assemble all of this into one comprehensive report that can serve as the basis for future research. So the first thing we did was assemble all the CECs together, and we found that there's 127 different chemicals that have been detected in the wastewater, which is high, but the actual amount is probably higher. This is just what's been studied for so far. It's highly dependent on the location. In North America, they found 88. And what's kind of interesting, North America is the only one that has found CECs that are not pharmaceuticals. So they're looking at a very wide range of contaminants. In Europe, there was 40. In Australia, there's 27. There was a few CECs that were consistent throughout all the continents, but not too many. But even amongst those, there was huge variations in the concentrations. So looking at the hit rate of the different CECs, we find that most of them are pharmaceuticals, which not too surprising because it's ingested by humans and then released into the wastewater. But there's also a fair share of others. Many of these are the ones that are really dangerous. Hormones are known to have a lot of issues, flame retardants, industrial chemicals, they're known to have a very detrimental impact. So it's important to look at all of them, not just the main group. So when you start looking at the CECs that were detected in North America, you find that even each chemical has a huge variation in concentrations from treatment plant to treatment plant. This is largely dependent on the city that is serviced, what the population makeup is. So older cities, or cities with older population will have certain types of chemicals, cities with younger populations will have different types. It also depends on if it's industrial, rural, different things like that. What is kind of concerning are the chemicals that spike up off the charts. For example, example, this one that has two spikes, iohexol, is a X-ray contrast media that it's basically the metallic-looking chemical that you drink to do an X-ray so they can highlight different parts of your organs. And it's designed to pass right through the human body without being absorbed or being changed. But that also, when it goes through a treatment plant, does not change. So it's very low removals, but once it hits the RO membrane, the molecules are so big they can't pass through. So it's just concentrated into the brine. So that becomes a major issue, and that's why we see such high rates of it. Looking at other ones too, there's very common amoxicillin. Anything that's used to fight infections, those are very, very common medications to find in the water. When we flip over to Europe, there's some similarities, but quite a few of these are unique just to Europe. And as you see, the same trends of variation of concentrations for each chemical. When you look at the anti-inflammatories, you see the same thing. Clarithromycin, very similar purpose to erythromycin, and once again, very high concentration. When you look at Australia, they have one or two CDCs that are common in other places. All the rest are different. They have a very unique makeup with theirs. But there's also not much research done there. There's one facility that tests a very select group of scientists, and they've only published a couple things from there. So their database is somewhat limited. When you take all of this and put them side by side, this is what it ends up looking like. And as you see, there's a lot of red, which is the Europe concentrations. Europe is known for having stronger wastewater than the United States, mainly because of the density of the population. It's been studied over and over. Their treatment plants have to deal with this. It's a major issue. There is a few chemicals that spike in North America, but as you notice, there's almost no orange up there. Australia, theirs are across the board very, very low concentrations, which is probably an inverse of the Europe situation. They have a lot lower population density, so you end up with the weaker wastewater. Some of this variation can also be attributed to different measuring practices and different dilution practices, if they're mixing it before measuring it or after. So that does explain some of it, but it's not surprising that Europe is stronger. So going through all of that, we found several indicator compounds that we do recommend. I won't go through all the names, I probably can't say most of them right. But we tried to pull one from each of the main families, based purely on how frequently they were found, if they were found in every test, and if the levels were at detectable ranges. So many of these are also reported as being the most dangerous. Carbamazepine, gemfibrozil are two of them that are known to have health impacts, so they agree right with our research. And there's also the need to look forward. The antibacterial triclosan is slowly being phased out of the pharmaceutical, by the pharmaceutical manufacturers. It's probably going to take about a decade, but it will have to be, right now, it's a very good indicator chemical, but in the future, it's probably going to have to be replaced by some other antibacterial. In addition to these, we also recommend 4 hormone indicators. Mainly, these are the 4 main hormones. They are well known for their health impacts on the environment. These are actually the ones that will cause the feminization of fish, so they are very important to monitor. These are actually more monitored than all of the other CDCs combined, so they are a concern, and the industry is aware of it. So after we went through that, we started looking at the available treatment options. This would be an additional treatment system just for the RO brine flow in order to either increase the recovery rate or to protect the environment and mitigate the impact on the body that's receiving chemicals. But the biggest thing is it has to be cost effective. Now CDCs are removed by three different removal mechanisms. Adsorption is where the CECs bind to the removing agent, such as in this picture, activated carbon. That's a very powerful tool. Biodegradation is where microorganisms will actually eat away and break down the compounds. And oxidation is a chemical breakdown of the compounds. Different CECs are vulnerable to different ones of these. There's no one that is successful against every single CEC. So we started looking into that, and these are the treatment methods that have been studied and that employ different variations of those three topics. All of these are common. None of them are too abnormal. They're all typically employed in either wastewater or water treatment. There was nothing too surprising there. But I'll go through them one by one. The first is the simplest and most cost-effective system, and that is coagulation flocculation. It involves dosing with a coagulant such as alum or ferric chloride, and it's very popular because it's low cost, easy to implement, easy to run, and it's been shown to have high removal rates of dissolved organic carbon. Unfortunately, tests have found that there's almost no removal of CECs. Research is still ongoing to find something that does offer removal rates, but as of now, the most common ones don't do anything for it. The next one is activated carbon, which is used in both a powdered form, where it's dropped into the water and allowed to pass through the treatment plant and then removed in the filtration process, or a granular activated carbon, where it's actually a carbon filter, a carbon bed. These have been found to offer very high CEC removal rates. On many, it's greater than 90%. So it's very promising. And studies have found that other contaminants start breaking through the carbon before CECs do. So you can monitor it easily without having to really monitor the CECs. It can be tracked quite well. It does have several issues. Carbon requires very lengthy contact time for the absorption process to be successful. And it also, once the carbon is spent, you have to do something with it, either regenerate it or dispose of it. But there is research that points towards lower flows in the RO brine may make this less of an issue because there's less of a need for less carbon need. Slight variation of this, biologically activated carbon, or BAC, is very similar. It's the same activated carbon bed, but they actually allow a microorganism community to grow in the carbon. The CECs enter into the system, and the bacteria will break down what CECs they can, and then those pieces are absorbed into the carbon. It's a very effective treatment method because it combines multiple mechanisms, and it offers very large range of removal, but it does have problems with CECs that aren't removed by either of those methods. So it's not perfect. There is a concern for high salinity and unknown operating parameters, but research is pointing that both of those are not as big of a concern as was originally believed. This brings us to the two most powerful ones. The first is ozonation. It's a very powerful oxidant that is very popular, especially in drinking water disinfection. It has been found to break down a very wide range of CECs very well, but it does have problems with those that are designed to not be oxidized. Some industrial chemicals are just passed right through this process. It also has an issue with the creation of the disinfection byproduct NDMA and Romeyn, but both of these can be mitigated by applying a correct ozone dose, as well as using either ammonia or peroxide, or some combination of the two, in order to prevent this. The general view in industry is this is the ideal method, mainly because it's cost effective, but it's not the most powerful. The most powerful is UV peroxide. This is very well known, one of the main systems used in OCSD's GWRS system, which is the world standard on water reclamation facilities. It offers a very broad removal rate, only if you use the peroxide. If you don't dose with peroxide, the removal rates are almost nothing. It does have a very high operational cost. The energy demand is huge, and replacing bulbs is very expensive. But there's actually a company in Arizona that is working on a replacement of current UV systems that harnesses the UV and heat from the sun to reach UV levels that a typical manufactured system can't touch. So I had a really good discussion with them. They found that it removes a lot of other chemicals in the water, but they haven't tested it on CDCs yet. So it'll be interesting to find out how that goes. But the Department of Defense is starting to implement that system, so there'll be some backing behind that, and hopefully that provides a very good solution. There's also the best method currently is to combine these treatment systems. Microfiltration before UV peroxide, or the biologically activated carbon after ozone. This pairs systems with opposing strengths to offer very good removal rates, but it does increase operating costs and maintenance costs. You have multiple systems that you have to take care of. There's also some future options that are under development. Many of these are membrane and thermal based. A lot of them rely on heat to remove the chemicals, which is a concern. Anything that's heat requires energy, and that gets expensive quickly. Many of these are intended for one specific chemical. Mining operations, for example, use this type of system, but it's not very good across the board, so they're not very frequently used. The one treatment method that is very promising is forward osmosis. This is very similar to reverse osmosis, but it doesn't use pumps. Instead, it uses salt, which most of the time is ammonia, is put on the clean water side, and the ammonia will actually pull the water through the membrane and then is easily boiled off. So there's just a slight increase in the temperature. Its boiling point is far lower than the boiling point of water. So just slightly increasing the water, it comes off and the water's clean. And then you still have to clean the membrane with, and you'll have brine off of that, but it's a much more efficient process. The main issue with this is it's been the technology of tomorrow for the last 20 years. They just can't quite get there and make it work. Currently, the biggest problem is the membranes are too difficult and too expensive to make for it to even be possible to use. But talking to several people in industry, they felt that it could be employed for brine stream treatment more effectively than other options because of the smaller flow. They can use a smaller membrane, it'll be more cost effective. So it'll be interesting to see where this is. Several manufacturers are just starting to get to the point where they're testing them. So in the next few years, this could become a major player, and eventually it could replace reverse osmosis as a whole, but you'll still have the brine issue with it. So all of these treatment options are driven by regulations. It's kind of how this industry goes. But currently, there's very limited CEC regulations. The EPA has the CCL list. It's currently in review for version 4. It has 108 chemicals, but these are just chemicals they recommend to watch. There's no guidelines or reporting limits or anything on that. The most stringent is California's State Water Resource Control Board, which is one of the big players right now in trying to find a solution to California's drought. They do have some regulations on CECs, but they're not too far into that field. They have a lot of other concerns on their plate. So it's very limited regulations, but they're the most thorough in the world. Outside of the U.S., the World Health Organization, who does a lot of drilling wells for very impoverished areas, has guidelines on what chemicals to look for as far as heavily contaminated water, but it's nothing that's very thorough. But in the future, there is going to be more regulation. It's just how things go in the water treatment industry. A lot of it's going to be driven by more precise measurement equipment. I was talking to a rep from Hawk that does monitoring equipment, and he said they just came out with a piece of equipment that can detect is it 3 drops of CECs in a swimming pool the size of the LA Coliseum. So it's getting close more and more to that point where it's really okay for human health, but it's being reported, which comes back to the whole public image. Is it safe? Is it not safe? So we really need to achieve a better understanding of CECs to make sure that there is no problems with this. So in conclusion, we found that brine CECs do pose potential health risk, but mainly to the aquatic wildlife that's exposed to the flow. The impact to human life is, unless you're drinking the RO brine, is pretty much negligible. Studies have been conducted on typical treatment plant outflow, and they found that the CECs in that were orders of magnitude below any sort of a human health threshold. So it's really not too much of a concern, but it has been found to impact aquatic organisms, so it is a concern on that end. Treatment is going to be driven by regulations. As of now, there's very little concern in industry for the brine treatment. They view it as it's already undergone secondary treatment, so it's not really a problem. It would be pretty much the same as typical treatment plant outflow, but they kind of overlook the fact that it's at a concentrated level. So there's a lot to be done there to change the mindset of whether or not it's worth even looking into. But currently, brine treatment is on a case-by-case basis, largely dependent upon the conditions of the receiving body of water. But as anything else, the cost is a huge concern. If it's too expensive, it just won't be done. So that's the main reason that a lot of the future options they're trying to find a more cost-effective method. So our project does have a few implications. The Bureau of Reclamation approached us with this project, and it also serves as the basis for a future project. This project is a treatment plant in Texas that discharges to a water with potentially sensitive areas, somewhat wetlands type areas. There's also a lot of projects in industry that have a concern with CECs. They're discharging to bodies of water that may end up in drinking water, so they want to know. One example of that is Sonoma County in Northern California has a treatment plant that is all ready to go, but they're scared to flip the switch because they don't know if that water is going to have an impact on the river that it's being discharged to. So we did expose industry to our findings as well. We presented at 4 conferences. Sophia and Wesley presented at the STIR conference for undergraduate research in Fullerton in November of last year. And I presented at the AMTA AWWA membrane conference in Orlando in early March. And then at the end of March, I presented at the Water Reuse Conference in LA and the AWRA Specialty Conference in LA. Both of these had quite a bit of industry interest. There was a lot of really good feedback, people coming to me after the presentation that wanted to discuss it, wanted to know what our findings were. And I compiled a list of some of the companies that we talked to. All of these companies and owners are facing issues where this is becoming a real problem. Many of the cities are having to deal with the public being really concerned about this. Metropolitan Water District's huge water distributor, it's becoming a real concern of theirs. And a lot of the consultants are having to include this in their reports. The one company here that helped me incredibly and is a leader in this is SPI. They're based down in San Diego. They basically have the closest thing to a plug-and-go reverse osmosis design as is possible. They are leaders in that realm. They're very good with monitoring for CECs and studying this type of industry. So they were very excited to hear that universities are starting to look at this. So to get further exposure to industry, we are pursuing publishing. The Water Science and Technology Journal is a peer-reviewed journal published by IWA Publishing. The impact factor for the journal last year was just over 1.2, which is the high end of the middle of impact ratings in the water realm. The highest is about a 5.3, but it's nearly impossible for a student to get published in that. And most are on the order of about 0.5 to 0.8. So we tried to go for something a little bit more aggressive than that, that would be a little bit more read and cited. So we submitted our findings about 3 weeks ago. It's gone through, been accepted to be reviewed. It's currently on its second week of review, and we're hoping to hear back sometime in the next 2 weeks. And they'll issue changes they want made, hopefully largely just spelling. We'll make the changes, resubmit it. It's an iterative process until we get a final paper that we hope is that everybody agrees upon and is publishable. But we're hoping to have that done by this fall. So we'll see how that goes. I do want to extend a special thank you to the Bureau of Reclamation for their support in this. Without them coming to Cal Poly and presenting this idea, I would be doing something completely different for my project. And this was a great experience. I learned a tremendous amount, met a lot of great people in industry, and there was a lot of interest. Cal Poly was very recognized in this. Metropolitan Water District was very, very excited that Cal Poly now has a master's program in the environmental realm. So, and that was the director of engineering with them that I was talking to. So he was very excited. I'd also like to thank my co-authors, Wesley Harihanto, who unfortunately couldn't be here today. He actually just started a new internship, and they don't let him leave before 5 o'clock. So he wasn't able to make it in case of bad timing. Sophia Sandoval has been very helpful. Saeed Delaga with the Bureau of Reclamation was the one that kind of has been overseeing everything, making sure that we're staying on track and that the Bureau is getting what the results that they're hoping for out of it. And then, of course, Dr. Ali Charlotte, my advisor, he's been very helpful. I also want to thank Cal Poly Pomona for letting me do this. I know it was a little bit of strain for them, but that was definitely, their support was greatly appreciated. And Skanska USA Civil for allowing me to work around my schedule. I know there's a lot of times where I have to leave early and come in very tired because I've been doing homework all night, but I do appreciate that. And of course, I have to thank my parents. Didn't expect that, huh? Without their help, there's no way I could have done all this. So I definitely am very thankful for that. So with that, I'd like to open up the floor to any questions that there might be. We have a couple minutes for dedicated questions.
Well, first,
Well, thank you so much. Interesting. I like the slide before this. So we have about
That was the last minute, Matt.
Yeah.
I was like, oh, I'll go for it.
So before we get into the questions, great work, thank you. And the sponsor for the project was Bureau of Reclamation and Saeed Delaga from Bureau's office from Denver, Colorado, is here today with us. He flew down here to attend this presentation. Also, we had a bunch of meetings and stuff today. And well, feel free to ask any sort of questions. I have already asked my questions, and I'll try to finish it. Like, we have time, we have 20 minutes. So.
you said that in one of your slides that the carbon had a 9% removal rate. Were you communicating that about the concentration itself or the CECs or a combination of them?
That's mainly concentration on a majority of the CECs. There are still a few that get passed through, but that system is a very encompassing one. There is a lot of concern with it, though, that it's expensive. Having to replace the carbon gets expensive. So it's not ideal for the high flows involved, like Hyperion. There's no way that any of those flows can be treated with carbon. So it's a concern, but that system has been proven for so long, it's kind of a good fallback. There's been a lot of research done on it.
Now, when you said 9% removal, you were talking about the type of removal. Do you know what the removal rates for them was? I mean, like, is it going from, like, can you quantify that in log removals, or is that just something listed in the literature?
Most of the removal rates are given in percentages.
Okay.
With activated carbon, most were above about 80% of a decline. That, a lot of that comes down to if the concentration was very, very high, it may be a larger removal rate just because there's so much of it, or if it's lower, it might be through. So, it's mainly 80% or above with activated carbon.
Okay,
That's
so
kind of the
operational,
rule of thumb.
operational differences will change the removal rates. Okay.
And the treatment processes before it.
Okay.
If it's being fouled by other things, the removal will be an issue.
I do have another question. You were talking about the treatment, say like forward osmosis. You were talking about how water comes through the membrane, and then it's the ammonia boiled off. What happens to the water after that?
The clean water?
Okay.
The clean water that passes through the forward osmosis?
Yes, or for that matter, any of these processes where the water is treated and that there is a stream of water that comes out of it that is not brine, but is not potable.
Most of that water is reintroduced back into the system. So it's becoming known as ZLD, zero liquid discharge. They're trying to get it so there is no brine discharge. If you have an RO plant inland, you don't want to be dumping brine in the local river, and you don't want to be dumping it in the ground. So they're trying to make it so you can recirculate as much as possible. So most of that will end up back at the beginning of the plant to go through the treatment processes again. And the hope is that a large portion of that will pass through the RO membrane and go on to be clean water.
Thank you.
Well, Don, you gonna raise your hand?
Oh, yeah, no, you go first.
I'll ask him a question, you go there. So you said you got industry knowledge in the part of this process? So I imagine you did like a survey of some sort, or did you just talk to people, or?
Yes, so we created a short survey, 1 page, that we sent out to treatment plants. Of all of the people I met working on this project, the treatment plants themselves were the most secretive. Which kind of surprised me. You'd think they're a public agency, they have knowledge that they're willing to give out. But they were very concerned about their name getting out there. They didn't want their information to be used in a negative way against them. So they were very worried about that. Consultants were actually the most open. They were, SBI, for example, I called him and he said, oh yeah, we have all these reports, I'll send them to you. And he mailed me a huge package with reports that they'd done over the last 10 years. And I was going through them and finding all sorts of really great information. So talking to them led to a few more findings, but we did have a few treatment plants that came back. Not all cases is the RO water being used for drinking water. A lot of it's being used for cooling of equipment. And in that case, there is no concern for CECs. It's all about salt content, because you don't want to corrode the pipes.
Go ahead, no.
Oh, I actually have to, with the forward osmosis, if you're using ammonia and you're boiling it off, you generate anhydrous ammonia that way. But you're putting in contact with water, then would that be a safety concern in operations?
That is something that they've thought about. I don't know exactly what the solution is to that. That would be more of like a byproduct type concern. But the forward osmosis is really promising. There's a lot of little things like that that have been a concern.
Oh, okay.
So, but yeah, that's a good point. When you boil it off, there's chemicals involved that are not exactly perfect.
Are you looking to extending SRT before sending the water to RO?
Yeah, so that's one thing that the industry, in a lot of ways, views as a solution. They try and keep the water in the treatment plant longer if they know there's a lot of CECs to try and get it to break down more. My initial research was actually in that realm. Before I started this project, I was looking into that. And there's some proof behind it that if you let it sit in a aeration basin longer, it'll break down more. But there's still some that just don't break down at all. And then there's still never 100% removal, because you have other parameters you're worried about. Trying to build a larger and larger basin to hold all that flow becomes a problem. So it has been looked into. talking to West Basin, they get water from Hyperion, and they said that when Hyperion is run a certain way, they have better results in their system than when it's run a different way. So they're trying to work with them to get, and I'm sure Chris is familiar with that. That does have a very big impact on what you're finding in the brine and in the effluent from the reverse osmosis.
What is SRT, for those of us who are not in the industry?
I don't know what the S is, but the RT is retention time. Or sludge retention time, that's what I was thinking, standing. So it's how long the sludge is left in the secondary basin. So if it's left longer, the idea is the bacteria are stronger and they're more developed and they can break down the chemicals more.
So when you looked into that forward osmosis stuff, had anybody actually built a desk size or maybe even a bench size treatment process at all?
I've heard of a few, basically desk-sized ones, but none of them that were still around. Most of them were built early 2000s, tested, and then scrapped. There was 2 or 3 of them, mainly because the membranes, they just couldn't keep them working. It requires a different membrane process and they break down really bad. So they said that with the funding they had, it wasn't possible to continue. There is some interest now that the membrane manufacturers are catching up with technology, of them starting to do those type of tests. But I don't know of any specific ones that are going on right now.
You talked about the zero liquid discharge facility. You talked about how the reconcentrating or the removal of water. At what point in time is there some type of discharge of the unwanted chemicals, and how does that take place?
So a lot of the things that are used on like mining operations, that's a problem. They end up building up tons and tons of salt or many gallons of acid that they have to discharge. That's a problem with electrodialysis for one of them. It has a byproduct of acid. A lot of the time that they try and sell the byproducts, but there's only so much acid needed in the world, and the salt it has CECs and other aggressive chemicals in it. So it does occur on a regular basis, based purely on the operating parameters, how much they're pulling out of the water. But it is a big expense that a lot of places try to avoid. That's why they're trying to, with the idea with the ozone and UV, is to break the chemicals down so they can just circle the water back in and have it break down, turn it into its constituent components, and maybe they'll break down more in secondary systems. Biological treatment may break it down more.
So you're saying that there's potential that there could be a recirculation within other types of treatment processes beyond that primary set of treatment processes. Okay,
Yeah.
so it could be like a multi-layered treatment process down the road.
Yeah, there's a lot of treatment plants that will send it all the way back to the beginning of the plant, and on the way back they'll put it through some sort of an additional treatment process to get it more into a state that they want it to entering the beginning of the treatment. So it's not going to poison the system or anything.
Sorry, just a full question. You had talked about the CECs and a detectable range, and I noticed one of them was ibuprofen. So the detectable range, noticing that one of them is one of the things we use on a regular basis, how does that relate to what it is that we use? I mean, like what is considered a CEC compared to what we consume?
So pretty much anything that is a manufactured chemical is considered a CEC, and then hormones, even if they're naturally occurring. Ibuprofen is one of the most common. We did find that a lot, but it's not as dangerous as the other options. If you think about that versus like a plasticizer, the plasticizer is far more dangerous. So that is what kind of drives which ones are concerned about. the detectable limit for each and every chemical is based on that chemical's properties. So some of the chemicals, it's much, much higher than other ones, based purely on makeup of the chemical.
Thank you.
Since he's asking about that, help me out with the vocabulary here, Travis, because I have heard of pharmaceutical and personal care products in the literature, PPCPs. So how does CECs compare to PPCPs?
CECs is more encompassing.
So
It
we got-
includes those, but it also adds industrial chemicals and pesticides and things like that.
So if I went and started pumping groundwater out of the Central Valley and stuff, then I would get CECs more related to ag runoff.
Yeah, herbicides, pesticides, it'd be much more common up there.
Okay.
And you'd end up with fewer of the pharmaceuticals and things like that. PPCPs was an older term. When it was first being discovered, that was the term they had coined it, and then they wanted to broaden it, so they added, they turned it into CECs, which is currently the name that it goes by. Who knows if down the road it'll expand it further.
So if we are hip, we must use CEC.
Yeah,
Got
that's one way to look at it.
Another question, disinfecting byproducts, do those fall under CECs or are they a different classification?
Different classification. Mainly because they'll be a result of the treatment process. They're kind of looked at as being separate.
Okay.
Did I see flame retardants up there?
Yes.
Where's that coming from?
So a lot of the industrial chemicals are discharged by industrial manufacturers. So they end up going down the drain or places like that. Some of that comes from old pipes. If the pipes were coated with asbestos, for one. I've recently heard that even with modern piping, you still get a leakage factor of anywhere from 10 to 15%. So the water can get out, but the chemicals are also able to get in. So it's a big concern. And I actually heard once that in Atlanta, they have something like 30% of their wastewater that enters into the storm drain leaks into the ground before it gets to the treatment plant. So if that's leaking out, all sorts of things are getting in. Don't know if you want to drink the water at Atlanta anymore.
I have one final comment to make. Travis, I'm from the Reclamation St. Eulalia, and we funded Travis and Professor Chevron for $10,000 in seed funding to start this project. And the level of effort that he's put into this project has been impressive. We gave him a very simple idea of CECs, what are the effects, and this is the result of this study. He basically made this in what it is. And now it's led to many additional projects and many additional works that are going to be coming out of it, because it's an area, concentrate is an area, especially concentrate in reuse, is an area that is part of being studied. Earlier this week, I was at a water reuse research conference on research, and everybody is talking about the endocrine disruptors, the CBCs, the PPCPs, and whatever acronym you want to attach to it, that is in the drinking water aspect of it. Nobody is talking about what's coming out of the concentrate, the ecological effects, the side effects that we would be causing by discharging these compounds in a concentrated form, and either on surface water, into ocean water, or into groundwater, whatever choice is on the concentrate. So thank you for your efforts. You've done a fantastic job, and look forward to seeing more work.
Thank you. Thank you everyone for coming. I do appreciate the support. It's been a lot of work to get to this point, so.
What are you doing?